So in the last class, we did this slide, right? The energy stored in a capacitor. So we have three equations. They are all identical. Depending on the question, you can use one of these three equations. Right. Then let's go to the next slide. Some applications again. So we know that a capacitor can store energy. And we saw one of the applications, the camera flash. Now another one is called the defibrillators that's used in the hospital. So there are some patients whose heartbeat is not regular pattern. So such patients, you can have an electric discharge from the capacitor which has been charged slowly and it is being discharged, and the electric energy through the heart can return this heart to its normal beat pattern. So one application. In general, capacitors act as energy reservoirs that can be slowly charged and then discharged quickly to produce a large amount of energy, so that is needed to jumpstart the heart, and the heart will get back to its regular pattern. Just an application. Right, now again more on capacitors. So usually when we talked about the theory of the capacitor, we said there are two plates, okay, parallel plates, so it's called the parallel plate capacitors, and between the plates you have nothing, air. Okay, so that's air is the insulator. So that's what we need, because there shouldn't be any current through the gap. So it's only a transient current. Then the capacitor plates become charged. So that's the usually happens. We can anyway between the gap we can put an insulator. It doesn't have to be air. Rubber, plastic, they are also like air. They are insulators. So the current cannot flow through the gap. So we call that as a dielectric. Okay, it's an insulator, but it has a special name when you place it between the capacitor plate. We call it dielectric. It's just an insulating material that when placed between the plates of a capacitor increases its capacitance. So it's a nice, because with the air, it may have a certain capacitance, but when you put this dielectric in, the capacitance will increase. So the amount of increase by a factor called kappa, this is actually looks like a K, but it's a Greek letter kappa, equivalent to the letter K, but a Greek alphabet. Even it is written like the K, but it's not exactly, there is a small difference, a Greek letter, kappa. So if it is just air, you will have the capacitance given as epsilon 0 A over D. But when happen, we put the dielectric between the capacitor plate for the same capacitor plates, it will increase by this factor kappa. Kappa is a value greater than 1 for any dielectric material other than air. So we have a name for this constant kappa. Do not confuse with the K, the Coulomb constant, no. So it looks more like a capital K, but written with the same size as the small letters. Kappa. It's called the dielectric constant. So let me repeat, do not confuse that with the K, the Coulomb constant, it's not the same. It's called the dielectric constant. That is by what factor the capacitance will increase when you put a dielectric between the two plates. So we can demonstrate this, why this capacitance, we can observe the capacitance actually increase when you put a dielectric. So this is, we have a capacitor plate let's say it's capacitance C0, and it has a charge that is inside, say, Q0 initially. So you know the C0 by definition is the amount of charge divided by the voltage across the plate. So we can use a voltmeter to measure the voltage. So it will say, okay, it is record certain value. Let's say it's recorded 2 volts between the capacitor plate. The charges on the plates is Q0, and the voltage difference or the potential difference between the plates is delta V. Then we slowly insert a dielectric, replacing the air. Before it was just air or vacuum. Now we put a dielectric between the plates. We don't change anything else, just put the dielectric, and you will see something. The voltmeter will read a smaller potential. So that's what this dielectric does. When you put the dielectric between the two plates, suppose the initial the potential difference was without the dielectrics 2 volt. The moment you put this dielectric in, it will reduce. So now if you want to know what the capacitance is, by definition, is the charge doesn't change because it's not going anywhere. Voltmeter just measures the potential difference, divide by the new voltage. Let me call it delta V. Here, let me call it delta V0. Delta V currently is less than the delta V0, the initial voltage. Now, you can see in the display, it has reduced from 2 volt to 1 volt. So that will tell us the new capacitance would have increased because what is in the denominator, the delta V is in the denominator, has decreased. So the capacitance should be increasing. So this is illustrating the point, okay, by putting a dielectric between the capacitor plate, the capacitance of the capacitor will increase. Now, why it increases? Because by putting this dielectric, somehow the potential difference across the plate has decreased. That will make the capacitance to increase. About this dielectric, we have a property called dielectric strength. For a given plate separation, there's a maximum electric field that can be produced in the dielectric before it breaks down. So we have a dielectric. Even if it is air, there is a dielectric strength for air as well. So if we keep increasing the potential difference, that will increase the electric field between the plate. So if you make it very high, say we connect it to a battery of, say, 1000 volts or something, at one point, this will start discharging. It will break down. The electric field is too high, so it can conduct the electricity through this dielectric. If that happens, it's not a capacitor anymore. So we say the maximum electric field at which this happens, the dielectric breaks down, so it will discharge electricity or it conducts electricity, is called the dielectric strength of this dielectric material. Beyond that value, you cannot use it as a capacitor because it is conducting after that. The current flows through the gap, through the dielectric material. So you should know the meaning of what is dielectric strength for a dielectric material. Commercial capacitor designs. So, commercially, actual capacitors that are available doesn't look like just two plates, because there are, practical use, we should have a very large capacitor. So we can have some flexible, we call the tubular capacitor, something like that. Here we have a metal foil, that is a plate, and a dielectric material, and again the plate, metal plate, and dielectric material, again the plate. It's like having capacitors in parallel, one above the other. And plus this is a foil, thin foil, these metal plates are. So it can be rolled, it's flexible. So we can economize the space, okay? We can have a very large capacitor in this manner in a small space by rolling it and making the volume small. So these are commercial capacitor design. And there is another one here. Here we have these other plates. Again, you can say these are parallel capacitor plates. So they add up. When you have capacitors that are in parallel, the equivalent capacitance will be simply the addition of it. So we can have many capacitors connected parallel like that. And here, the insulating or dielectric is the oil. What is between the two plates? Oil is an insulator, so it will act as the dielectric material. So another design here, this is called an electrolytic capacitor. It's a bit different from the rest. So what we have here is the metallic foil. And on the metallic foil, you have an oxide layer, thin oxide layer. So, and then an electrolyte. So let me use some colors so to make it clear. So electrolyte, the liquid, right? So this is, the electrolyte is one plate. It's a conductor. And the foil, metallic foil, okay, I need to draw it neatly. Okay. This is, the liquid itself is one plate, it's a conductor, electrolyte is a conductor. Then we have okay, the metallic foil, okay, this is the other conductor, the two plates. And where is the insulating material? The insulating material is the oxide layer, which is very thin. On top of this metallic foil, you have the oxide layer, and the conductor should touch the oxide layer. This is the conductor, electrolyte solution. So the red one is one plate, which is the electrolyte solution. It is not the dielectric. And the green one is the other plate. And on the green metallic foil, you have the oxide layer. The oxide layer is the gap between the two plates. So the oxide layer can be very extremely thin. So that make the D, the gap between the two plates, to be very, very small. That will make the capacitance, this D is very small. That means the capacitance will be very big. So that is the advantage of the electrolytic capacitor, can have a capacitance in the range of farads. 1 farad means very large capacitance. It also has polarity. I don't want to, if it connect it in one direction only, it will be a capacitor. In the other direction, it can, it can break down. It can destroy the circuit. So you have to be careful with the electrolytic capacitor. The connection polarity is very important. Right, now we will explain why the capacitance increases when you put a dielectric, by an atomic description of the dielectric. When you put this dielectric in, polarization occurs in the dielectric material. So I will show it in the next screen as a picture. You know what is polarization? Polarization means when there is a separation between the average position of the negative charge and the positive charge. We talked about it before. So in the dielectric, when you put it in a capacitor, because there's an electric field, there is a charge separation. Charges, one plate is positive, other plate is negative, so there's an electric field. So this dielectric become polarized because of this electric field. So this field produces an induced polarization in the dielectric material. So I will show it with a picture here. So here is the capacitor plate, the positive plate is red, and the negative plate is negative. So now what happens, this dielectric material in the middle, those molecules will become polarized. So closer to the positive plate, you will have the negative charge average position will be shifted towards the positive plate like this, and the positive charge will be away. On the other side, near the negative plate, the opposite will happen. All right. So this will be making induced polarization in the electric field. So you can kind of see this will cancel, this will cancel. That means you will have here a positive end in the dielectric material and a negative end in the side closest to the positive plate in the dielectric material. So this will make an electric field in the opposite direction to the electric field from the capacitor plate. So the effective electric field between the plate will decrease. The electric field will decrease. That's why you see the potential difference between the plates is being decreased. We saw it in the demonstration. So if you connect a voltmeter between the plates and you put a dielectric between the plates, the potential difference decreases. The reason is this. Because of the induced polarization, the dielectric material will produce an electric field in the opposite direction. So the net electric field between the plates will decrease. That will decrease the potential difference. So that is the mechanism of this, how the dielectric material reduces the or increases the capacitance by reducing the potential difference between the plates. Right. So that finishes this chapter. Now, what we will do is to solve questions. I will open the midterm 1 exam, which is posted in the Moodle. This one, not the last year, this is the one before last year. Okay. Thursday, yes. Exam is on Thursday. So I believe I solved this chapter 15 question. So since we just finished chapter 16, I will go to chapter 16 question. Yeah, this one. Question number 12. There are exactly 11 questions from chapter 15 and 11 questions from chapter 16. So 12th one is a question from chapter 16. So this question is about electric potential energy and potential. As a proton moves in the direction of the electric field lines, so let me draw electric field lines. So let's say there is electric field lines from going from left to right like this, and you take a proton, let me put like that, and say it moves from point A to point B. So along in the direction of the electric field, one thing you should remember is, if you have electric field lines, if you move along the electric field line, what happened to the potential? Increases or decreases? Decreases. Positive plate is at a higher potential. Negative plate is at a lower potential. So electric field line is always from the positive to negative. So you can imagine a capacitor plate, just if you forget that, you can imagine a capacitor plate, and you remember in a capacitor plate, we have a uniform electric field going from the positive plate to negative plate. And you know, positive plate, remember, positive plate is at a higher potential, negative plate is at a lower potential. So the electric field line, when you move in the direction of the electric field line, potential decreases. Remember that, okay? If you remember that, you can answer this question easily. So that is one way of remembering it, by picturing a capacitor plate. So Suppose this proton, a positive particle, proton is a positive particle, move from A to B in the direction of the electric field. Now you can tell me, I mean, it doesn't depend on the charged particle. If there is an electric field, the potential is from potential decreases in the direction of the electric field. So potential at A, in my diagram there, is greater than the potential at B. So when the particle moves, it doesn't matter whether it's a positive particle or negative particle. It doesn't, potential does not depend on the particle that you bring in. Potential will decrease in the direction of the electric field. So that you know. So here we are looking at potential, also potential energy. We are looking at both. So you know when you go in the direction of the electric field, potential will decrease. So that part I know. So A, if you read A, as the proton goes from A to B, it doesn't matter it's proton or whatever, potential will be from high to low if you move in the direction of the electric field. Therefore, this is wrong, right? Because this says low to high. So it is wrong. B, it is moving from low to high. That is also wrong, just because of the potential. When you go from A to B, it doesn't matter what is that particle is, whether it's a positive particle or negative particle, it doesn't depend on the particle. By itself, the potential will decrease when you move in the direction of the electric field. C, yeah, this could be correct, but we don't know about this, right? So we keep it. D, this could be also correct because high to low, but we don't know about this yet. I'm not looking at. What about this? We don't know. Let me now talk about the potential energy. Potential, you know, it doesn't depend on the charge that you are moving. When you move in the direction of the electric field, potential will decrease. Okay, let me ask the opposite. If you move in the opposite direction of the electric field, potential will increase. Okay, so now what about the potential energy? All right, now let's look at what happens to potential energy, whether it decreases or increases. We found the potential decreases. Now what about potential energy? You know this relationship between potential and potential energy. It comes from the definition of potential in terms of potential energy. So we can write that relationship here. Change in the potential energy equals charge into change in the potential. So now it's very clear that we have a relationship between how the potential changes with how the potential energy changing. We have a positive particle, and when the potential changes in some way, the potential energy will also change in the same way because Q is positive. So if delta V is positive, Q being positive, delta PE also will be positive. In our case, we have a positive charge and we have the potential energy to be decreasing. That tells us potential energy will decrease. So that leave out of these two choices D to be the correct choice, because D tells you high potential is decreasing and potential energy is also decreasing. Losing means it loses its potential energy, so it starts from a higher potential energy to lower potential energy, losing potential energy. Number 13. A particle with an electric charge of 3.40 coulombs, so this is the charge, is moved in a system, within a system. As a result, the electric potential energy changes from 2.5 to 1.35 nanojoule. The electric potential at the initial position of the particle is the V initial. Potential is V. Potential energy is PE. What is the electric potential at the final position of the particle? So here we are talking about, how we connect the potential change to potential energy change. So that should ring a bell. You should remember an equation which connects the potential energy. Oops, the other way around. Okay, potential is defined in terms of the potential energy like this. Maybe it is easier to remember it this way. I don't know which one is given in the formula sheet. It doesn't matter. So the potential change and the potential energy change is given by this equation. All you have to do is to just substitute things into this equation. Identify what is being given. Q is given, right? So there is a Q in the formula, the charge. And he is giving, what is this? It's an energy, initial energy and the final energy. So that is PE. So this guy will be potential energy initial. And this guy will be potential energy final. They have sign, okay? Energies have sign. No sign means it is positive. If you want to say it is negative only, you need to put the negative sign. Otherwise, it is understood, it is positive. So what else? What is this? This is the electric potential, that means V at the initial. So this guy is V initial. All you have to do is to just substitute. There is only one unknown in this equation. What do you mean by delta potential energy? Mean potential energy final minus potential energy initial. These are given. And Q is given. Delta V mean V final minus V initial. V final is not given, V initial is given. The question is to find the V final. So there is only unknown in this equation. So I can write that out. Delta P will be, tell me, 1.35 nanojoule. I will ignore the units for the time being, but I'll tell you. And 2.50 nanojoule. Nanojoule is not SI unit, right? Joule is the SI unit. Well, something you will not be given is what is nano. You should memorize. 10 to the power minus 9, okay? Milli is 10 to the minus 3. Micro is 10 to the minus 6. Nano is 10 to the power minus 9. Also in the positive side, kilo is 10 to the plus 3. Mega is 10 to the power 6. Giga is 10 to the power 9. These 369 up and down you should memorize. Right. So I didn't write here. I can write together here. 10 to the power minus 9. And Q is 3.40 nanocoulomb. Again, 10 to the power minus 9. And delta V, I will write V final, which is the unknown, minus V initial, which is 3 volt. That is a SI unit. See, look. You already have the answer, right? Because there is only one unknown in this equation. And also, you don't have to put the nano. It cancels both sides. Now, you take your calculator. And put it in. You don't need to worry about algebra. So you can start a, you don't need this. Bracket is not needed. That's the only thing. So 1.35 minus 2.5. Okay, that's the only operation we have on the left-hand side. There's no need for the brackets. Equal. Oops, that's not equal. Where is equal? Okay. Okay, equal 3.4. Now you need to put the multiplication and start the bracket. Here it is important. So VF is the unknown. So you use the X for that. Alpha, not alpha, is it alpha? Shift, right? Okay, sorry. I need this. Is it alpha or shift? Shift, yeah. No, alpha. You want the x. Okay, that is alpha. Alpha x minus 3. Close the bracket. You got the equation. All you do now is to tell the calculator to solve for x. So shift calc, that's not the answer. It is something that was in the from previous operation. So you have to press the equal button. There you should see this L minus R. Then only x is equal to 0.66. That's right. Okay, that's the answer. So we'll continue. Right. I will delete this because this thing is. I'm recording the lecture, so I'll post it later. Right. This is an easy one. Okay, I tend to give this again and again. So electron volt is a measure of energy when the energy is very small, like in the atomic scale. So this is the useful energy for measuring energy values. Joule is too big in the atomic scale. Number 15, electric potential at a distance of 4 meters from a certain point charge is 200 volt relative to infinity. What is the potential at a distance of 2 meters from the same charge? Now, here, if you don't remember, there is an equation for a point charge for potential, you would be in trouble. I mean, you should know the theory. It's not because I have the formula sheet, I can do anything. You will be in trouble. You should know which equation to pick. So although I am helping you by writing description, this is the potential formula for point charges and so on, that will help you, but don't treat it like some you have to remember this and plug and chug, then you're not learning any physics. You should not just memorize, you should understand what you're doing. So for a point charge, we have a formula for the potential energy. Potential. Okay, we are talking about potential, not potential energy. That is another thing you have to keep in your mind. Okay, a field that is coming from an electric charge, you have something called electric potential. It doesn't depend on bringing in another charge. Okay, there's no interaction between another charge. It's not like that. It's just a property of the electric field created by some source. So if you have a point charge Q, there's electric potential field everywhere in the space. Say at a point R distance away from this charge, it is given by this formula that you should remember. If you need to remember immediately, there is a formula for the potential of a point charge given by this equation. Once you remember that, your physics part is finished. Then it's just a matter of some algebra math. So what the question says is, when R is a certain value, the R1, at certain R1, V1 is given. R1 is 4 meters, V1 is 200 volt. For a certain R1, the value of V1 is given. Then he says, what is the potential? This is at R1, which is 4 meters, at a distance of 2 meters. It is the same anywhere in that distance. So when R2 is 2 meters. So what we are doing here is the same charge. We don't change the charge for the same charge. And we don't change the K is a constant. K is a constant. So it tells you the dependency on R is 1 over R. So when you decrease the R, potential should increase, right? As you go, because 1 over R, inversely proportional. So what do? 4 meters become 2 meters. So you halved it, right? So what should become the V2? same Q. So R1 previously 4 meters, now it become 2 meters. This is equal to 200, and what should that V2 be? It should increase. When you make it half, V2 should become 2 times. It's not R squared, right? Be careful. For electric field in a magnitude, then it's not R squared, it's 1 over R only. So there's no squaring or anything. So when R1 is halved, V2 must become twice. So you can look at it in, this is just thinking it out, but you can do it mathematically without much thinking. You can see that VR is a constant. VR is a constant. K is a constant, Q is a constant, same charge, and K is a constant. So you can say V1 R1 is equal to V2 R2 because they are inverse relationship. So the product is a constant. If it is direct proportionality, the ratio is constant. And that's it. You are being, this is given, this is given, this is given. Unknown is V2. We can put it like that as well. Okay. So this is kind of, if you know this trick, it will become faster. In an exam situation, if you know some tricks like this, it will help. So you do without thinking too much, you get it. But this is not in the formula sheet because this is not general. This become true only you are talking about the same charge. Okay, here we are talking about the same charge. Right, this one, question number 16. Two point charges are situated on an XY axis as shown in the figure. Charge Q1 is unknown. Point P is located in the first quadrant, a distance R1 from charge Q1 and a distance R2 from charge Q2. The values of the charges and their respective distances from P are is asking for two things. Well, it's given, and he is asking for what is Q1 equal to. This is the question, the value of Q1. How do we find it? So it is, there's a little twist. Usually what we'll be asking, what is the potential at P? Okay, that's a direct question. Here we give the potential, net potential at point P, but we don't give one of the charges. Not this one. This charge is not given, asking for the Q1. But you have a calculator, you don't do algebra or anything, you just write the equation and tell the calculator to solve for it. So our superposition principle we have for volt potential difference, a potential at a point P, Q1 will have a potential at point P, let me call it V1. Q2 will have its own potential at P, let me call it V2. And the net potential, if I call it V, it will be V. So this is the equation. So is this equation in the formula sheet? No. This is simply we are applying the superposition principle. That means what is the potential at P? There will be potential coming from Q1 and a potential coming from Q2. So the net potential at point P will be the potential that is coming from charge Q1, let me call it V1, plus the potential that is coming from Q2, let me call it V2. So if you look for this equation in the formula sheet, you will not find it. So if you don't know the theory, you don't know where to start. So in the question, he is saying the total electric potential at point P is this. That means he is giving this. And he is saying anything else? He is giving us the R1 and R2. R1 is the distance from Q1, so this is given. And R2, the distance from Q2 to this point, that is also given. Additionally, Q2 is also given, but Q1 is not given. Should you, I mean, usual question will be, they will give Q1 R1 and Q2 R2 and find V. That's a direct question. What is missing? That's something I didn't tell you. The equation for the potential from a point charge. So we need this equation. And do you see this equation in the formula sheet? No. That is the principle of superposition. If you have two charges, the net potential will be potential from Q1, that is V1, and the potential from Q2, that is V2. When you add these two, you will get the total potential. So the question technique is changed. I gave you the total potential, and I'm asking to find the value of Q1 without giving Q1. Now I can write the equation in full. V is given, right? 4.1. Is it SI unit? Yes. Joule per coulomb. This is V. V1 is what? V1 will be K Q1 divided by R1. V2 will be K Q2 divided by R2. Is this given K? Is not in the question, but in the formula sheet, right? 8.99 10 to the power 9. So you know this. Is this given? Yes. Is this given? Yes. Is this given? Yes. Is this given? No. Is this given? This is not given. Is this given? Yes. How many unknown? Only one unknown. So, without the normal pattern is, you will give Q1 R1 and ask you to find the total potential. Yeah, there's a small twist. You give the total potential and make something else as the unknown. But, I'm not testing you for math. You get the equation, that is the physics part, formulate the question, then you take your calculator. That's it. So let me do that for you. Right. 4.1 exponential 4, that is V, equal sign, alpha equal. Then I will use this one, that is useful, okay. K is 8.99 exponential 9 multiplied by Q1, that's the unknown. What do? We call it X, right? Alpha, right parenthesis, that's X. Now bring it down, R1 is given, 0.845, okay, 0.845. You cannot complain the math calculation is too much. You are not doing any algebra, right? You just use the calculator in solving mode. Bring it up. One thing I have to tell you, don't forget this Q must be substituted with the correct sign. Did I do that correctly? Well, X is not given. We don't know what it is, okay? So plus K and R has no sign. R is a magnitude only, the distance only. Again, I use the fraction. K is 8.99 exponent 9 multiplied by Q2. Yeah, it's with the negative sign. So you must put this bracket, otherwise you'll be in trouble. Because if you use without the bracket, you put the minus, it is going to get confused. It will think it is, I don't know, it will be problematic, okay? So you must put the bracket and choose this negative sign, this one, and 5.86. You should know how to use this exponent thing. Minus 6. This minus 6. Close the bracket. So I hope you are following me. Anyway, I'm recording this, so you can look at it later. So come down. R2. What is R2? 0.65. 0.65. You think, okay, it's a very complicated equation to solve, but you don't do anything. You just tell the calculator to do it for you. Job done. So what do? Let me just check it is okay. Yeah, it's okay. I didn't make any mistake. That's very important. The bracket is there within the bracket and multiplication. What do? Shift calc. That's not the answer. This is from the previous calculation. Press the equal button. There it is. 1.14 and the minus 5. That's right? It is rounded to 3 significant figures. So 147 become 15. Okay, good. I will clear this. It is being recorded, so don't worry, I will post it. Number 17. 2 point charges of 2 microcoulomb and negative 2 microcoulomb are located 1.5 meters apart. What is the minimum amount of work needed to move the charges to make the distance between them to 2 meters? So we have 2 charges, Q1 and Q2. They are 1.5 meters apart initially. Okay, this is the initial scenario. Then we move these charges, maybe one of the charges, to make the distance greater. So now with the same 2 charges, the distance is, before it is R1 is equal to this, R2, we change the R, now it is 2 meters. These are both, one is positive, one is negative. We need to do work. Sometimes it will be negative work, sometimes it is positive work. We don't know. We need to do work to do this. Sometimes it will do by itself. Without we doing anything, the electric field will do a positive work, so the work we do will be negative. But sometimes, you have to force it. Okay. What do you think in this case? You have to do a positive work or negative work? Why? No. This is initial. Then it is like this initially. We don't do anything. It is there. Okay. Now I have to separate them. To do that, you have to do work, or it will do it by itself. Yeah. Because they are attracting each other, right? So I am separating them. If you want to make it less, it will do by itself. But it's a 2 charges, positive, negative, will be attracting. So I am breaking them, making them far away. That means I have to do a positive work. The answer must be a positive answer. Anyway, we didn't give any negative answer. So, right, now, how do I answer this question? The conservation of energy, change in the potential energy plus the change in the kinetic energy is equal to the work you do externally. We have this system of 2 charges, and you are doing some changes to the configuration. And when you do that, we need to put some work. So the work will be how much the potential energy change from initial to final, how much of the kinetic energy change from the initial to final. Now we are saying minimum amount of work. So we are not changing the kinetic energy. So we don't worry about changing because the minimum amount of that implies we are not changing the kinetic energy. We slowly move it with a 0 to 0 kinetic energy. So there is no change in the kinetic energy. So anyway, you are being helped here. So you only get the change in the potential energy to get the work done. How much work you have to do to make this separation? That means there will be certain potential energy in this configuration initial, and in this configuration, the potential energy will be different. If the potential energy final is greater than the potential energy initial, that means you are doing a positive work. Change in the potential energy will be positive. So this means now we need the formula for potential energy of two charges. It's in the formula sheet. Okay. Anyone can tell me? Potential energy of 2-point charges when they are in a certain distance away. It is potential energy, not potential, not V, PE. No, you're not talking about kinetic energy. Potential energy is something we learned in chapter 16. When you have 2-point charges in a particular distance away, the potential energy of that two-particle system is given by this formula. Please check your formula sheet. So now you can the connection. So that's it. You substitute. So that will be K, Q1, Q2 is the same before and after. R1 final first, right? So R2. Potential energy final minus potential energy initial. So R2 is what is final minus K, Q1, Q2, R1. Q1, Q2 didn't change. K is a constant. That is a matter of substituting the numbers. You just take your calculator. If you want, you just make the calculation a bit simpler. K, Q1, Q2 is a constant. Say common factor. This expression also, you can do a little bit of algebra. That helps you. Algebra is very important. Okay, don't ignore that. You as scientists, engineers, algebra must be the basic algebra must be strong. You have no substitute for that. So K, Q1, Q2, 1 over R1, R2 minus 1 over R1. We can just do it now. I want to simplify it a little bit. If you don't like this simplifying, you can just put everything in the calculator as well, no issue. So let me get my calculator. I'll clear the stuff. K, tell me what is K? 8.99 exponent 9. Multiply by Q1. Okay, you have to be careful with the units, right? Also the sign. Okay, sign of the charge is very important. It's not magnitude. You have to put with the correct sign. So Q1 is positive, good. And it is microcoulomb. Microcoulomb is not SI unit. Oops. So you better convert that to SI unit. Let me put a bracket also just to make things clear. Because this doesn't have a negative sign, but just I want to be, make it more systematic. 2 exponent minus 6, right? Minus 6, close the bracket, multiply, that is Q1. So I need this one really need the bracket because of the negative sign. Minus 2, use this negative, 2, it's also 2, exponent, micro mean negative 6, close the bracket. So I got the K, Q1, Q2, multiply. Now I need a big bracket for 1 over R2 minus 1 over R1. So start the bracket. Then I will use this fraction. Okay, 1 over R1. 1, come down. What is R1? 1.5. Bring it up. Minus, again, this fraction. 1, bring it down. 2. This R is magnitude. Okay, R is magnitude. They don't have sign. 2. Close the bracket. That's it. This is not even equation solving. It's just execute now. There's no X's here. X is the subject. Okay. What did I do? I did something wrong. Let me see. I was thinking of an equation or what? What did I do? No, I didn't put any equation. 8.99 10 to the power 9, 2 into the minus 6, minus 2 into the minus 6 into 1 over R1 minus 1 over syntax error. I don't know. Let me look at it. Okay, right. 8.99. This one. I forgot to do the exponentiation. I did something. Is it exponentiation? No, that is correct. 8.99 to the power 9, 2 into the minus 6, minus 2 into the minus 6, multiplied by 1 over 1.5 minus 1 over 2. It's not minus? Probably I used that. Oh, yeah, it's not minus. I used the negative sign. Okay, right. I hope. Yeah, right. I used this guy there. It's a subtraction. I need the. Yeah, you saw the size of this. Right. So you make it SD 0. That's correct. You know what is going here? It is given in millijoule, not joule. This is in joule. So how do you convert the joule to millijoule? You have to multiply by 1000. Joule to millijoule. So it becomes 0.006, 6.99, which is 5.99, which is to two significant digit, it becomes 6.0. Right. I'll go to the next one. Which of the following statement is not correct for a charged conductor in electrostatic equilibrium? Right. So you need to remember the properties of a charged conductor. In chapter 15, we talk about electric field inside is 0. Any excess charge will come to the surface, and the electric field on the surface will be perpendicular. And then the number 4 is at sharp corners, there will be more charges, more density of charges compared to the smooth corner. Then when you come to chapter 16, you have added property, which is a conductor. Everywhere in the charged conductor, it is the same potential on the surface as well as inside. So if you remember that, you can just, not correct. That's another thing you have to. So all of them are correct except one statement. So when it is correct, you ignore it. You look for the one that is not correct. Let me look at A. The electric field is 0 inside the conductor. That is correct, right? Therefore, I cannot choose it. C. All excess charges reside on the surface of the conductor. That's a property of a conductor. That is correct. So you don't choose it. D. The electric field just outside the surface of the conductor is perpendicular to the surface. That is another property. So you don't see it. It's correct. Therefore, you don't choose it. Potential everywhere inside the conductor is constant, also equal to the value inside. Inside at the surface. So that is also correct. B. The surface of the conductor is neutral, because he is saying it's a charged conductor. That means there is an excess charge, and those excess charge actually go to the surface. So the surface of the conductor is charged, not neutral. So that is wrong. So that's why we picked that. Number 19. Parallel plate capacitor has been charged. So that one plate has positive charge, other plate has negative charges. In the thin space between the two charged plate, what do the electric field lines look like? So this is a basic. You either know it or you don't know it. The electric field between them will be straight lines like this, going from the positive to the negative. Just remember this diagram, this picture. So the electric field lines are perpendicular to the plate. Yes, correct. and they are directed from the negative to the positive plate. That is wrong. Okay, it is perpendicular to the plate, but the direction will be from the positive plate to the negative plate. So this is wrong. Let me look at this. The electric field lines are parallel to the plate. No, it is perpendicular plate. So it is wrong. D, the electric field lines are directed 45 degrees. Wrong. D, there is no electric field. Wrong. Okay, if that's a charge, the separation, they will be charged. So there will be electric field. So B is the correct statement. Number 20. Charge on the square plates of a parallel plate capacitor is Q. The potential across the plate is maintained with constant voltage by battery as they are moved closer together to make the distance between them 1/3 of their original separation, which is small compared to the dimension of the plate. The amount of charge on the plate is now equal to. Okay, now here we have a capacitor plate which is connected to a battery, and we keep it connected to the battery. Okay, it is connected to the battery. Now what we do, we move this plate closer, keeping the battery connected. Before this distance, let's say 3, now the distance is 1, because 1/3, right? 1/3 of 3 is, if suppose I put some value 3, then make 1/3 of 3, 1/3 of 3 will be 1. Before the charge is Q, what is the charge now? So Q0, what is Q? It will change because there's a battery that is connected to it. So when you decrease the capacitor distance, the capacitance will increase because the capacitance is given by epsilon 0 A divided by D. It's air between, no dielectric, so there is no kappa. We change the distance, we bring it closer. What happens to the new capacitance? This is C0, this is D0. Now you make it smaller. Are we changing the epsilon 0? No, it's a constant. Are we changing the area of the place? No, he doesn't say. We only change the distance. So if this is 3, now new, it will be, this is before it is 3, now the new D will be 1. What will happen in the new capacitors? Increase or decrease? Yeah, it will be, because you are dividing by a smaller number. So this initial one will be 1/3 of the new one. So the new capacitance will be 3 times the old one. Not the capacitance, I'm sorry. So we still have, he is asking for the C will be 3 times. Okay, but the question is not the C. The question is what is Q. So we have one more step. From this, I see the capacitance become 3 times the old capacitance. Then we go to the equation for capacitance. Capacitance definition is Q divided by delta V. So Q is equal to C multiplied by delta V. Are we changing the potential? It's the same battery. So if C is 3 times higher, Q will be 3 times. This is a Q0, C0. So the new Q will be 3 times C0 delta V, the same. So the Q will also be 3 times larger than before. Okay, maybe one more question. I can finish it. 21. Yeah, this is easy. It's just a technique. You know the technique, you can do it very quickly. What is the equivalent capacitance of these? They all have the same capacitance, phi. So this is phi, this is phi, this is phi, this is phi. So what is the, can you replace the whole thing by just one capacitor? And if so, what is that value? That's the question. You go step by step. You recognize these two are in series. Is any question in that? These two are in series. No question with that. Can you see anything else that is in series? No. Only. Can you see anything else that is in parallel? No. Only thing that is clear is these two are in series. So I can replace these two by just one capacitor. So I'm going to cancel this, cancel this, cancel this, and get phi and phi in series. What will it be? This is phi, this is phi. In series, it will be half of phi. Phi inverse plus phi inverse, the whole thing, 2.5. Okay. So I can replace these two by just one capacitor, which is 2.5. Now 2.5 and 5 are in parallel. That is clear. Okay, just 2.5, which is the equivalent capacitors of these two that I have cancelled one of them. These are in parallel. When you are in parallel, you add them. So 5 plus 2.5 will be 7.5. So I can get rid of all these three and put just one capacitor, which is 7.5. Now the 7.5 and 5 is in series. 7.5 and 5 in series. So I can get it as 7.5 inverse plus 5 inverse, the whole thing inverse. Somebody do it for me. You get 3? Come on. Don't have a calculator? Okay, here we go. Right. I'll start a bracket, 7.5 inverse plus 5 inverse, close the bracket, the whole thing inverse, right? You get the idea? 3, okay? All in microfarad, the answer is in microfarad. Right, the last question. That's a straightforward question. You have an equation for energy stored in a capacitor, which is given as U half Q delta V. That's the first one. Can I use this? Is Q given? No. Is delta V given? Yes. But Q, so I'm going to use this. This is given. This is given. You ask him for Q. So I just, I assumed I know the question already. I didn't read it carefully. So he is giving the energy. 43.4 joule is the energy. So you substitute the energy 43.4 equal to half. Q is our unknown. Delta V is 9. Just solve for Q. So you should get the answer 9.64 Coulomb.